Hi all, welcome to Finisq Analytics. Today we are going to learn about the famous Black-Scholes Merton model, which is heavily used for option pricings for the equity asset classes. Now, this is one of the lecture in our quant finance series, wherein we will learn the derivation of the Black-Scholes partial differential equation and then how we will come up with the closed form solution of the BSM. So for that, I just created a story so that it can entice you, it can make you more relatable. Now, this guy is a genius quant wannabe, a trader who is preparing for his interview for his quant round with one of the bulge bracket investment bank, Goldman Sachs, on their equity desk side. So he is interested in knowing, is there anything through which the option prices, right, can be figured out, and thereby he can do trading with an intent to generate some P&L for the bank. How the world of equities and options works, on which mathematical rules? So yes, there is. We can definitely figure out how the world of equities and options works, what are the basic mathematical rules, and trust me, the BSM derivation that we are going to work upon today is the most basic thing that we are going to look into the quant finance. Though all the big bulge bracket banks have some advanced models which are nothing but just some tweaks or some modifications with the Black-Scholes. Now, what is the Black-Scholes equations? Black-Scholes equation is nothing but a partial differential equation with respect to its various inputs. As we know that the option price, right? Let's denote it via V. This is the option value, or you can say the price, right? It is dependent upon multiple factors. For example, the spot price, the strike price, time to maturity, dividend, volatility, risk-free rate. Am I missing anything? STKRTD sigma, right? Yep. So I think these are the six factors over which these are mainly the six factor over which the option value is dependent. Now, based on this inputs, Black and Scholes on their first original paper derive a partial differential equation which serves as the basics or most heavily used equation for pricing the options. When I say pricing the option, it is mostly used for pricing the European option and is as it is formed with some modifications around it, putting some conditions and relaxing some conditions. We can also work on the American options, but that is out of context over here. Yep. So the Black-Scholes equation is delta V by delta T plus half of sigma square S square delta square V by delta S square plus RS delta V by delta S minus RV equals to 0. Now, at first, this equation might look a bit intimidating, but please try to relate it with the Taylor series, wherein we have first order derivative, second order derivative, and the 1 factorial, 2 factorial. If you try to relate that with this partial differential equation, then you can make some sense out of it. Nonetheless, if you're not able to relate it, I will still try to make it more simpler for you. Now, economically, or I would say, if I just ignore the mathematical terms, Black-Scholes equation consists of basically four things. The first is the time decay, which is delta V by delta T. This, this, this guy, right? This is time decay. Now, this this one, half of sigma square S square delta square V by delta S square is nothing but the convexity term. Why convexity? Because it consists of your second order derivative with respect to the spot price. The third is the drift term, which is Rs deba V by deba S. It denotes what would be the growth in your spot rate or in your stock price with respect to the risk-free rate. And the fourth one is minus RV. Minus RV is the discounting term. Why you need to discount it? Because when I say the European options um, can be exercised upon a fixed expiry, right? But if you're trying to value it today, you need to discount it back with the risk-free rate. That's why it is minus RV. So economically, these are the four terms um, which make up the Black-Scholes equations. We are going to learn step-by-step derivation of the Black-Scholes equations, how we can derive it. This is something that I developed by my own. I'm not sure whether you are going to find it on an intranet or any book, but this is something that I find it easy when I want to quickly remember the Black-Scholes equations, or when I want to know how and what premises the Black-Scholes equation is derived, because this is more or less the way in which you should portray your answers when it's been asked on an interview regarding the Black-Scholes equations. Now, the original derivation of the Black-Scholes partial differential equation was via stochastic calculus, Ito's lemma, and simple hedging argument. This is being published by Black-Scholes in 1973 in its paper. So I'm going to use the same method through which um, we can derive these equations, and we can also backtest the results that has been produced by the Black-Scholes. However, just to let you know, there are more than 10 plus ways through which you can derive the Black-Scholes equations, but we will stick with the first, which is hedging and the partial differential equations. So I hope it is sound exciting to you. It is making some sense to you. So let's see how we will derive the Black-Scholes equations into the via different steps. Now, it's a four steps derivation. The first is to construct a portfolio. Second is applying arithmetic Brownian motion and Ito-Lemma applications. Third is when you have the portfolio, you know that it's having a property of ABM and Ito's application, then you will apply the delta hedging. When you apply the delta hedging, or for any portfolio, when you neutralizes your volatility or the delta hedging risk, right? That means your portfolio will grow by the risk-free rate, and thereby you can apply the no arbitrage principle. So these are the four steps which you need to follow to derive the Black-Scholes partial differential equation. Post that, it's just a mathematical beauty to arrive at the closed form solution of Black-Scholes Merton model. Now, the first is construct portfolio, ABM, Ito's application, delta hedging, and arbitrage principle. I intentionally have not created any slides post that, because I want to show you the live derivation of the Black-Scholes PDE. So let's walk over here. Now, let's say you have a portfolio which is denoted by pi. Sorry, and this pi consists of long options denoted by V, as we see, and some delta quantity of stocks denoted by S, which you shorted. That means you hold a short position on the stocks and you hold a long positions on the options. So your pi is equals to V minus delta S. This is your portfolio. Now we know that change in the stock price, DS, is given by the arithmetic Brownian motion, as I said, right, is given by mu s dt plus sigma s dx or dz, you can say. Now, this is the ABM, arithmetic Brownian motion. If you're not sure with the ABM, you can quickly refer to my earlier series on the arithmetic Brownian motion, geometric Brownian motion, and Ito's lemma. Now, this is the drift term, and this is the diffusion. Now, don't get confused by what is drift, what is diffusion. When I say drift, it is purely a deterministic term, and this is purely a stochastic term. Why stochastic? Because we have dz. dz is nothing but sorry, dz is nothing but Wiener process, which is a standardized Brownian motion process, and it follows a random walk, and it is nothing but epsilon, which is some noise, and the square root of dt, which is the tiny time interval. Now, we know that this is the basic equation of the ABM, right? The arithmetic Brownian motion when you want to predict the change in the stock price over a tiny interval of time, that is dt. Now, what would be the change in the option value whose underlying is itself following a random walk? For that, we need to apply the Eto's lemma and come up with the change in the option value over a very small tiny interval of time dt. So how we can do that? Now, dv, as I said, is nothing but delta v by delta t into dt plus half of sigma square s square delta square v upon delta s square into dt plus delta v by delta s into ds. This is by Ito's lemma. Just think that Ito's lemma is similar to your Taylor series. You all must have read Taylor series. If not, you can just Google it around. It is heavily used um, for the VAR approximations. So it is nothing but your if I just want to state on the mathematical terms, then this will be your f0, or I would say the original function value plus 1 factorial plus 1 by 1 factorial into first order derivative into change in the change that you applied to your function plus half arrives by 1 by 2 factorial into second order derivative, and then you just square the shock size. If this is not making sense, then please Google out what is Taylor series, then try to relate it with the Ito's lemma. Taylor series is for the deterministic world, whereas Ito's lemma is for the stochastic world. Now, since now we have dv, change in the option value over a small time period dt, change in the option this is the change in the option price, then we also have change in the stock price over a small tiny or tiny interval period of dt. Then what would be the change in my portfolio over a small time period? Then that would be denoted by d pi. D pi would be nothing but dv minus delta into ds. So it's just now we need to equate something, and then you need to shift the term, so finally you will arrive with this part, delta v by delta t plus half of sigma square s square delta square v upon delta s square dt plus d delta v by delta s minus delta into ds. So what I did is I just taken the dt terms together and ds terms together. Now, since ds term is having a randomness, You remember the equation that's been derived by ABM, randomness on account of DZ or the Wiener process. So to remove this for delta hedging, right, we need to do the delta hedging now. We already constructed the portfolio, we apply the ABM and ethos property. Now we need to do the delta hedging. So delta hedging is nothing but to remove the randomness. How we can remove the randomness? By choosing this quantity delta as equal to delta V by delta S. If this is delta V by delta S, then this term would be 0. So we will be left with just deterministic part, this. I hope it is clear till now, right? Now, so when we get rid of the randomness, what we are left is with d pi is equals to delta V by delta T plus half of sigma square s square delta square V upon delta s square whole with a small tiny interval. Now let's denote this as A. Now we get rid of the randomness, so obviously our portfolio is growing by a risk-free rate. That means the change in the portfolio would nothing but equal to risk-free rate into your original portfolio value over a small period of interval. Now this is equation B, and it is nothing but um, RFR driven change in portfolio, since your portfolio is now delta hedged. Now apply arbitrage, no arbitrage principle. That is A equals to B, and what you would get finally is delta V by delta T plus half of sigma square s square delta square V upon delta s square. Dt would get cancels out. R pi is nothing but V minus delta S, right? And delta, this delta is nothing but dV by ds into S. So what would be your equation? Your final equation would be, therefore the final equation would be delta V by delta T plus half of sigma square s square delta square V upon delta S square. Now you will shift this term which is minus over here, so there it would comes to plus delta V by delta S into ds into R, sorry, S into R, and this term, right, minus RV would come over here because that's positive there. So this is your partial differential equation of Black-Scholes, right? This is Black-Scholes PTE. Now, when you apply the boundary conditions to this equation, then at that time you will realize that you are ended up in the closed form solution of Black-Scholes Merton model equation. But this is the most important equation that you should keep in mind, because this will give you not just the option valuation but also the Greeks, that is equally important to measure the risk of your portfolio. In the next series, I will show you how you can apply the boundary condition, and then we will reach the famous Black-Scholes closed form solutions, which is heavily used for option pricing. Thank you.